Hello everyone, I am Dr. Debasish Das, currently working as an assistant professor at the Department of Mechanical Engineering, MIT Vishnupur, West Bengal, India. Today's topic of our discussion is study on melt pool fluid flow during welding. So, whenever we hear the term fluid flow, usually fluid mechanics comes into our mind. Then, what does fluid mechanics is doing here in the study of welding process? Actually, when beam impinges on the workpiece and some melting occurs, at that microscopic zone, some melt pool fluid flow occurs. So, this is studied in the present discussion utilizing two techniques. First one is the CFD based phenomenological model, and second one is the analytical equations. These are some of the well known equations which are studied during high school and graduation. These will be used to study the fluid flow occurring in the melt pool. The purpose of this study is to identify the role of convection on heat transfer and its influence on macro and microscopic weld attributes such as weld geometry and spiking and microhardness, secondary ferritic arm spacing, coarsening coefficient because of chromium diffusion, etc. This is the reference. Now, whenever we hear the word fluid flow, different macro and microscopic forms of fluid flow which occur in our day-to-day lives comes into picture. For example, the water sources we used in our toilet, washroom, etc. is one form of fluid flow, while suppose imagine a raging river where the water is turbulent. That type of flow is having a different nature. So from very small scale to very large scale, we have different nature of fluid flow. Now, these are the type of fluid flow which we can observe in day-to-day life. We humans have a tendency to simulate whatever is observed in experimental conditions. Therefore, three different fluid flow conditions are simulated here. At the left side, we have simulated a condition of which is used for testing of aircraft. Here, the influence of air pressure on wings are studied, which is a macro scale study. Next is a micro scale study where the fluid flow occurring in the blood vessel is simulated. And third one is an intermediate scale where water flow is simulated. Now, if we are simulating different aspects of fluid flow, then why not welding? We have the provision to simulate welding using this CFD based phenomenological model. Many researchers such as David et al., Mishra and Debra, Mundra have used this phenomenological model to predict temperature, melt pool flow velocity, weld pool geometry, and various forces acting in the melt pool. Now, the equations utilized in the CFD-based phenomenological model include momentum equation, continuity equation, then transportation equation, Marangoni convection forces, boundary condition, and finally heat flux which is acting at the top of the surface. Now, moving to the analytical modeling which deals with some formulations, popular formulas such as Reynolds number, Piclet number, Prandtl number, Grashof number, and Archimedes number. These numbers are used to study the fluid properties using analytical technique. Next, the advantages of studying fluid flow is discussed here. It helps us better understand the mechanism of melt pool fluid flow condition. The nature of fluid flow is correlated to the macro and microscopic weld attributes. The nature of convective heat transfer is better understood, and innovative solutions of traditional welding problems from the perspective of fluid dynamics is presented here. Now, moving to the observation sector, in the present study, we have studied the influence of three different heat inputs, that is low, intermediate, and high heat input on fluid flow attributes. Initially, the mean flow velocity is obtained from the CFD-based phenomenological model for the three said heat inputs. It is observed that as heat input increased, the melt flow velocity also increased. This data is used in different analytical equations where Reynolds number, Piclet number, Prandtl's number, and Grasshoff's number, all of these analytical models showed an increase in their values from low to high heat input. This indicated strong dominance of fluid convection on heat transfer. Next, the Archimedes number showed an inverse relationship. That is, for low heat input, its value is found to be highest, while at highest heat input, its value is found to be lowest. This also indicates melt pool convection as an effective model of heat transfer. Now, moving to the conclusion, the fluid convection was found to be important mode of heat transfer throughout the melt pool. Next, an increase in melt pool flow velocity, Reynolds number, Piclet's number, and Grasshoff's number corresponding to an increase in heat input is observed to increase this fluid convection. Disclaimer. Thank you very much.